So what we looked at in the last few videos is a situation where you have a restoring force that works in a very particular way, where the restoring force, like a spring, tries to restore the position or the displacement back to equilibrium with a force that's proportional to the amount of displacement. Now I want to consider a more general restoring force. So let's assume that you have a system where, I mean, it doesn't have to be a mass on a spring, but let's just say x of t is the displacement of something from equilibrium. So you've just got something, and there's an equilibrium position for it. Something can move in one dimension, and there's an equilibrium position for it. So there's a position where if it's there, then it will stay there forever. And there are forces on it in such a way that the forces are restoring forces. So if you displace it, then it'll try to go back. Okay? But I'm not going to assume that it goes back with strength proportional to the amount of displacement. I'm not going to assume that. So I'm just going to assume that f of x, so force depends on amount of displacement, I'm going to assume is a restoring force. Any kind of restoring force. So this is a really, really common situation. This is a very general setting. So let me write down sort of mathematically what's meant by restoring force. For f of x to be a restoring force, it has to be that if you... so when I say x of t is displacement from equilibrium, I mean x equals 0 would be equilibrium. So for f to be a restoring force, it would have to be that, first of all, the force when x is 0 is 0. So if I put in x equals 0, then I get 0 force. So that just tells me that x equals 0 is in equilibrium. And secondly, if x is greater than 0, then f of x, so if x is positive, if you displace in one direction, whatever direction is the positive direction, then it'll try to send x back. So f of x should be negative. And if x is negative, then f of x is positive. So this is all that's meant, basically, by f of x is a restoring force. Okay, so it does not have to be a mass on a spring, or it could be a mass on a spring, but you don't have to assume that it's this ideal Hooke's law kind of setup. It could be, it could be a pendulum, for example, and x of t represents the angular displacement from the pendulum just being down. That would be equilibrium. Or it could be, maybe there's two planets, and they're both attracting some particle, which is in the middle here. And if the planets have the same mass, and the particle is right in the middle, then that's an equilibrium. Well, actually, no, that's a bad example. That wouldn't be a restoring force, right? Because as you move the particle to the right, it would get accelerated to the right, and as you move it to the left, it would get accelerated to the left. So let's change that example. Imagine two charges, like a negatively charged thing here, a negatively charged thing here, same amount of charge, and then imagine that your particle is also negatively charged, so that it's repelled by both. Then if you try to move the particle to here, then it'll get repelled and pushed back this way. And if you try to move it to here, it gets repelled and pushed back this way. So that would be an example of a restoring force. But the magnitude of the restoring force would definitely not be proportional to the amount of displacement. It would be something more complicated having to do with how electrical forces work. So you would have to use like Coulomb's law or whatever works for electrical forces. Okay, so f of x is any restoring force. Then, this is the differential equation you would have according to Newton's second law. This would be your differential equation. Now, is this one of those differential equations that I described in the last video? Is this a second order linear homogeneous differential equation with constant coefficients? Well, I mean, you can rewrite it like this if you want to, and view this as L applied to x, but this definitely does not need to be linear. I mean, f of x could be complicated. Like, for example, what if f of x equals negative x squared? That's, oh, that would not work. How about negative x cubed? That would satisfy all three of these properties here. So that would be a restoring force. But the differential equation mx prime prime plus x cubed equals 0 is definitely not linear. This is not a linear differential equation. And part of the reason is the x is getting cubed. So linear differential equations linear second order differential equations end up only being allowed to look like this, where a, b, and c are allowed to depend on time, and you're allowed to have time on the right hand side here, but you can't have something like x cubed. So this is definitely not linear. So we do not necessarily end up with a linear differential equation. However, sorry, I didn't mean to erase that much. However, I want to convince you that the situation that we're going to study in depth is still useful here. So actually, let me erase that. If x is small, then we can do a Taylor approximation for f of x. We can do a first order Taylor approximation, so we can linearly approximate f. Like this. So if you imagine that you're making small displacements, x is close to 0, so small displacements away from equilibrium, then f of x, well, think about the Taylor series for f of x, centered at x equals 0. It would be f of 0 plus the derivative of f at 0 times x plus 1/2 the double derivative of f at 0 times x squared plus, and then higher order terms. That would be the Taylor series. But when f is assumed to be a restoring force, well, f of 0 is 0, right? So thanks to this fact that x is in equilibrium, f of 0 is 0, we don't have this, right? If we assume x is small, what happens when you square a small number? You get something very small, right? Intuitively, you would think, oh, when I square a number, the number gets bigger. That's usually people's first intuition. But if you square like 1/1000th, then you get 1/1,000,000th. And, you know, if x is, think about it this way, if x is something like 1/1000th, then this term is multiplied by x squared, which has a 1/1,000,000th, right? And adding a 1/1,000,000th type thing to a 1/1000th type thing is going to have a negligible effect. It'll go away in your web work rounding or whatever, right? This is not even going to matter. So this approximation is good if x is small. Let me actually continue my color coding here. So let's make x is small be yellow. And that's what justifies getting rid of all the higher order stuff. And finally, let me use blue for this part. this fact that when x is greater than 0, f of x is less than 0, and when x is less than 0, f of x is greater than 0, this tells you about f prime of 0. It tells you f prime of 0 is negative, right? I guess it could equal 0, but let's not forget about that case. This tells you that it's negative. If it does equal 0, then you shouldn't be doing this kind of approximation. But let's also pretend that f prime of 0 is not 0. Then it would be negative, according to these 2 points. So that tells you that this here is negative k for some positive number k, where k is defined to be negative f prime 0, which is less than 0, which is greater than 0. So look what we got. Just from assuming we have a restoring force and focusing on very small oscillations about equilibrium, so small x, we have, for our differential equation, mx prime prime equals f of x is approximately equal to negative kx, where k is positive. Wow, look at that. Mx prime prime equals negative kx. That's Hooke's law, right? That's Hooke's law, but you don't need to be looking at a spring mass system for Hooke's law to come in. So this system in general, this is called, so anytime you have mx prime prime plus kx equals 0, which is what we got here, this is called a simple harmonic oscillator. This is a simple harmonic oscillator. This is a really general setup anytime you have a restoring force. So this is one of the things that we're going to be able to handle once we finish chapter 2, or actually just next week we'll be able to handle this. And in fact, we'll be able to introduce damping. So when you introduce the damping, then it's called a damped harmonic oscillator. I don't think I've ever seen this abbreviation, but I'm just too lazy to write it.